Hello everyone. In this video we're going to be solving a nice exponential equation. We have x squared minus 7x plus 11 to the power x plus 1 equals 1, and we're going to be solving for real x values. I'm going to show you two graphs, one of which doesn't exactly belong to this function, but I just wanted to share with you what I found. Anyway, so we have this exponential equation. Let's go ahead and look at three different cases. And if we're looking for real solutions, basically, and let's say we have something like a to the power b equals 1, this basically gives us three different cases. First case, a can be 1, b can be anything. So let's say b is a real number in this case. Or a can be -1 and b must be even. It's an integer, that's even. And b is 0 and a does not equal 0. Because 0 to the power 0 is not 1. It can be lots of different things. Okay, so we're going to be looking at each of these cases, and like I said earlier, I'm going to show you a graph. Okay, so the base is a, so let's go ahead and start by looking at the first case. I'm going to call this the first case, this one the second case, and this one the third case. So our first case scenario, base is equal to 1, which means x squared minus 7x plus 11 equals 1. So, and at this point, basically our exponent is x plus 1, so you want x plus 1 to be a real number, but x plus 1 is always going to be a real number, right? As long as this equation has real solutions. What happens if the equation doesn't have any real solutions? Then it'll have non-real complex solutions, and in that case, x plus 1 is not going to be a real number either. So let's go ahead and solve this quadratic equation by putting the 1 on the left-hand side, subtract 1. And then you can solve this equation in so many different ways, not so many, maybe just a couple. One of them is quadratic formula. Another one would be completing the square, which is not recommended because the coefficient of x is not even. So that's going to be a little problematic. You have to deal with fractions. But anyways, the idea is, just subtract 10 and then add half of this number squared to both sides, which would be 7 halves squared, which is 49 fourths. And then 49 fourths, by the way, is greater than 10, so this is going to be a positive sum. And then this will be a perfect square, so on and so forth. That is completing the square stuff, okay? But I'm going to use the third method here, which is not always available, by the way, and that is called factoring. And the reason why factoring works here is because this equation has integer solutions. And some equations have rational solutions, and they are also factorable. So here's how it works. You got to find two numbers whose product is 10 and whose sum is -7. And those numbers, first of all, when you think about it, the product is positive and the sum is negative. The numbers both have to be negative. So you're looking at factors of 10, but they have to be negative factors. So -1 and -10, -2 and -5, -5 and -2, so on and so forth. By the way, the order doesn't matter. -1 and -10 is the same thing as -10 and -1. So we don't have to worry about those. And this is pretty much the only way to factor it. And among these two possibilities, this will work. -2 and -5. Make sense? So you basically go through the cases and find it. I wanted to walk you through this because a lot of times I just walk through with the solution as if I just find it on the first try, but that's not the case. Anyways, so the idea is to find two numbers whose product is 10 and whose sum is -7, and we found them. And then you can just kind of pair them up with x's and write it as x minus 2 times x minus 5. You can also break it down into x squared minus 2x minus 5x plus 10, and then factor this by grouping. It just turns out to be the same thing. But this is just a little faster. Anyway, so from here we get the solutions, x equals 2 and x equals 5. Since 2 and 5 are real numbers, this will definitely imply x plus 1 to be a real number. Make sense? So these solutions are going to be welcome. That's the first case. Let's go ahead and take a look at the second case. And what was the second case? The second case was for the base to be, so we've taken care of this, now we're doing this one. The second case was for the base to be -1. So let's go ahead and set the base to -1. And then we want the exponent to be even. So we want x plus 1 to be even. But x plus 1 is even only if x is odd. So you want x to be an odd number. Okay? Let's go ahead and solve this problem by putting the -1 on the left-hand side. In other words, adding 1 to both sides, plus 1. And then this is going to give you a 0 here. So we're going to get x squared minus 7x plus 12 equals 0. And then we're going to factor this like before, because this is also factorable. By the way, how could you tell it's factorable? You look at the discriminant, base b squared minus 4ac, and that's going to give you 1, which is a perfect square. When this is a perfect square, then you will have a factorable equation. All right, great. So let's go ahead and factor it. Find two numbers whose product is 12 and whose sum is -7. Again, those numbers are negative, and those numbers are going to be -3 and -4. So we can factor it as x minus 3 times x minus 4 equals 0. And from here we get x equals 3 and x equals 4. But only one of them is acceptable because we want x to be odd. Remember, x plus 1 is even. So x must be odd and 4 is not odd. It's even. So we can only take x equals 3. And from the other case, we got 2 and 5. So far, we got 3 solutions for this equation. Let's go ahead and take a look at the third case scenario, and then we'll conclude with the graphs. So let me copy the equation here. We have x squared minus 7x plus 11 to the power x plus 1 equals 1. And the third case is where the exponent equals 0 and the base does not equal 0. So here's one thing to keep in mind. This equation doesn't have rational solutions, and this equation has an integer solution. So we don't have to worry about this being 0, because if x is -1, obviously it's not going to satisfy the other equation. Make sense? So you can immediately dismiss the limitation, so we don't have to worry about it. Make sense? Hopefully it does, and x equals -1 automatically follows. And that's a good solution because it doesn't make the base 0. Okay, and if you don't believe that, you can go ahead and plug it in, and you're going to see that it doesn't make the base 0. Okay, so we got -1, we got 3, we got 2 and 5. Let's go ahead and list all these solutions with our curly braces, the nice set symbol, -1, and then 2, 3, and then 5. Now here's a good question for you to explore. Are there are there complex non-real solutions? Something to think about. Anyways, let's go ahead and take a look at the graph real quick. So this is the graph that kind of explains the solutions. And we kind of said, okay, -1, 2, 3, and 5 is a solution. Where is the 3? Oopsies, what happened to 3? Okay, something again to think about. Why don't we have 3 in this equation? Anyways, I wanted to show you another graph. Not that it's the graph of this equation, but a similar equation. But one of the things that Desmos does sometimes with exponential equations is it kind of starts graphing it with dots, but those dots are scattered because it's not always well defined. Anyways, this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.